So now what we've got are these two separate recall and precision measures, and separately they tell us something about the machine learning algorithms. But it's not very helpful to have these two as separate measures, because when we're trying to compare across our machine learning algorithms, it might be the case that we decide we care more about precision. So let's say I have two candidate algorithms, A and B, and A has outperformed B on precision. So say it's 0.7 to 0.8. So machine learning algorithm A has the point 0.8 and B has 0.7. So this is clearly, if I care about precision and I'm not taking into consideration anything else, I can say quite definitively that algorithm A is better than algorithm B. But what happens when I take into account my recall measures as well? And maybe the recall for algorithm B is significantly better than the algorithm A's recall. So how do I know then which one is better? How do I weight those? And obviously, individually, you can decide upon how you're going to weight the importance of these, but there is a kind of standard way of doing this, and we incorporate both of the measures into something that we call the F measure. So the most standard F measure that you'll likely encounter will be F1, and this just looks like 2PR over P plus R, where P stands for precision and R stands for your recall measure. So this is the equivalent of the harmonic mean, but more generally we can look at this thing called the F beta measure. So the F beta measure is essentially this. So on the numerator we have in brackets 1 plus beta squared all times by PR over beta squared P plus R, again where P is precision and R is recall. Now you can obviously see that when you substitute 1 in for the beta, you will get that harmonic mean again. So that's kind of how the two tie in together. What's more difficult to kind of see is the significance of beta. So what happens when you increase beta and when you decrease beta? Now, the intuition behind it isn't so obvious, or at least it wasn't obvious to me. But just to kind of let you know where we're headed, essentially it turns out that as you increase beta beyond 1, so as beta increases, you give more importance to your recall score. So if you care particularly about the recall for your use case, you're going to want to increase that beta score. And then as you decrease it below 1, beta actually gives more weighting to your precision score. This wasn't obvious to me, because if you look at that equation, it looks like, well, as beta increases, P increases, so it seems like that should be giving precision more weighting. But what we're going to do is basically rearrange this equation to make it more obvious. So the first thing that we should be looking to understand is, well, what do we consider to be a good score? Like, obviously, if we give more weighting to recall, we want to be able to say, well, therefore, with a good recall score, our F score is better. So what does it mean to have a good F score? Well, essentially, we're trying to get the F measure as big as possible. Now, as it transpires, the biggest it could possibly be is 1. So, as your rule of thumb, an F score of 1 is good and an F score of 0 is bad. But in terms of looking at this equation, it's enough to think, well, I just want to make this number as big as possible. And so therefore, what I'm really trying to do is make that denominator as small as possible, because obviously when you're dividing any amount of pi up between a number of people, the less people you have, the more pi everyone gets, e.g. the bigger that F measure is going to be. So the reason I'm going to rearrange this to kind of explain the intuition behind the relationship between the beta and the P and the R is because I personally find it hard to understand the relationship of variables when they're all over the place, and having them in your numerator and denominator is just all kinds of mind-boggling for me. So what I'm going to try and do is put these sort of in the same place. So that involves taking the reciprocal of PR. So, and this is basically the same as saying 1 plus beta squared over beta squared P plus R over, again, PR. You're just taking the reciprocal. And then, again, we've still got these P's and the R's in different places, even though they're both in the numerator. So what I've done next is just sort of separated those into two equations, so that we've only got 1P and 1R. And now we can see that the beta squared is actually connected to that R. We've got 1 over P plus beta squared over R on our numerator. And now it becomes a lot easier to understand what happens as you increase beta. So in this case, we know that as beta increases, what we're doing is giving more weighting to R, and that's because as beta gets bigger and bigger, the whatever score you have for R is going to have a bigger impact on the size of that of that numerator. So for example, if I made beta something ridiculous like 50, well, having a 0.1r is obviously going to have a huge impact on the size of that numerator. Versus if I have a small beta, so if I have something like 0.5, well, even if I have a 0.1 recall, that's still, a relatively small number. It's not nearly as big as the 50 over 0.1. Whereas precision is not affected by this at all. So as R has less impact on the lower beta, that must mean therefore that precision has a bigger influence. So that's kind of the intuition behind why the ranges for beta have the effect that they do on the relative weightings of precision and recall.